Optimizing LLM inference includes reducing the time to first token, or latency, increasing the number of tokens per second, or throughput, and minimizing the memory footprint of LLM. We want to maximize GPU utilization. However, naive deployment approaches lead to poor hardware utilization and underwhelming throughput and latency. Fortunately, a variety of optimization techniques have emerged to dramatically speed up inference. In this video, we'll cover KV cache, continuous batching, optimized attention mechanisms, and model parallelism that are supported in popular inference engines such as vLLM, TensorRT-LLM, and SGLang. Let's start with an outline. First, we'll talk about prefill and decode as the two phases of LLM serving. Next, we'll discuss KV cache, followed by continuous batching. Finally, we'll talk about optimized attention mechanisms and model parallelism. Most popular decoder-only LLMs are pre-trained on causal objective, essentially as the next word predictors. And during inference, each LLM serving request goes through two phases, prefill and decode. The prefill phase processes the entire input prompt and produces the first output token, while decode phase generates the rest of output tokens one at a time. The challenge is that token generation is inherently sequential. To generate the next token, you need to have generated all the previous tokens. Addressing this bottleneck is one of the core subjects of inference optimization. One common optimization of the decode phase is KV caching. Remember that to predict the fifth token in the sequence, the LLM needs to know the context of tokens 1 through 4. When predicting the sixth token, it again needs to know the information from tokens 1 through 4 plus token 5. This repeated computation can be cached in the KV cache shown on the slide. Basically, instead of recomputing key value pairs for each new token, the model retrieves them from the cache, significantly speeding up inference. When a new token is generated, only the key and value for that single token need to be computed and added to the cache as shown at the bottom. Efficiently managing KV cache is essential as it can quickly exhaust available GPU VRAM and limit the batch sizes that can be processed. This motivated the development of optimized attention mechanisms such as paged attention and flash attention. Two main contributors of GPU LLM memory requirements are model weights and the KV cache. Batching, or processing multiple inference requests simultaneously, is a standard approach to achieve high throughput. Larger batch sizes spread out the memory cost of model weights and transfer more data to the GPU at once, better saturating its parallel compute capacity. Batch sizes, however, can only be increased up to a limit, at which point they lead to a memory overflow. Traditional batching, also called static batching, is suboptimal. This is because for each request in a batch, the LLM may generate a different number of completion tokens, and subsequently, they have different execution times. As a result, all requests in the batch must wait until the longest request is finished, which can be exacerbated by a large variance in the generation lengths. There are methods to mitigate this, such as continuous batching. Continuous batching, also known as in-flight batching, aims to increase GPU utilization by feeding a new request into the batch as soon as the previous request completes. In other words, as soon as a request completes its generation, it is evicted from the batch and a new request takes its place. Continuous batching is natively implemented in most inference frameworks such as vLLM, TensorRT-LLM, and SGLang. The transformer architecture is based on the attention mechanism, which scales quadratically with the number of input tokens. This is particularly inefficient for long sequences. This motivated the development of optimized attention mechanisms such as paged attention and flash attention. Paged attention draws inspiration from virtual memory and paging in operating systems. It partitions KV cache into blocks, eliminating the need for contiguous memory allocation. This partitioning allows for near-optimal memory utilization. Another popular option is flash attention. Flash attention divides input and output matrices into smaller blocks that can fit into the GPU's on-chip SRAM, which is a much faster than high-bandwidth memory. This approach significantly reduces the frequency of data transfers between the GPU's main memory and its processing units. This is combined with online softmax, which computes the softmax function independently for each block of the attention scores matrix rather than for the entire matrix at once by maintaining a running maximum and a running sum of exponentials. Paged attention partitions KV cache into blocks so that internal and external memory fragmentations do not occur. Flash attention makes use of much faster on-chip SRAM memory compared to high-bandwidth memory. Model parallelism allows you to distribute the memory and compute requirements of LLMs across multiple GPUs. This enables the training and inference of models that are too large to fit on a single GPU, which also improves performance in terms of throughput, measured in tokens per second. There are three main approaches to model parallelism, each involving splitting the model weights and computation in different ways: data parallelism, pipeline parallelism, and tensor parallelism. Data parallelism is the simplest type of model parallelism. It involves making copies of the model and distributing these replicas across different GPUs. Each GPU processes a subset of the data simultaneously. During training, the gradients calculated on each GPU are averaged and used to update the model parameters. During inference, data parallelism can be used for processing concurrent requests. However, this technique works when the model is small enough to fit into a single GPU. Typically, data parallelism mainly used for training, while pipeline and tensor parallelism are preferred for inference. Pipeline parallelism is a strategy for distributing the computation load of LLM training and inference across multiple GPUs. Pipeline parallelism partitions the model's layers across different GPUs. This allows each GPU to handle a specific portion of the model, reducing the memory burden on individual GPUs. As shown on this slide, the model is divided into 4 segments, with each segment assigned to a different GPU. During the forward pass, activations are computed and then passed along to the next GPU. For training, the backward pass follows a similar sequence in reverse, with gradients propagated back through the GPUs. The main limitation of pipeline parallelism is that due to sequential nature of the processing, some devices or layers remain idle while waiting for the output, activations or gradients, of the previous layers. These idle times can be seen as pipeline bubbles, pictured as empty areas where no processing takes place. Microbatching was developed to mitigate the impact of pipeline bubbles. By splitting the input batch into smaller sub-batches, microbatching ensures that GPUs remain busier as the next sub-batch can begin processing before the previous one is fully completed. Tensor parallelism is another popular technique that distributes computation across multiple GPUs. Tensor parallelism splits the weight matrices found in individual layers such that each GPU holds a portion of these matrices and performs computations on its respective slice. Attention blocks and MLP layers are major components of transformers that can take advantage of tensor parallelism. Data, pipeline, and tensor parallelism are orthogonal techniques that can be combined. For example, a model can be split depthwise into a few pipeline stages, with tensor parallelism used within each stage. Other techniques for inference optimization include model quantization, and we'll cover that in detail in another video. Thank you for watching. I hope you enjoyed this video. If you're interested in more educational ML content, please hit like and subscribe to my channel. Looking forward to seeing you soon.